Now, I know quantum numbers can be yucky and confusing, and they're more really for PChem and when you get really into the math of where those electrons are. So we are going to actually represent them most of the time in a different way. We're going to write what are called electron configurations. And before we write those electron configurations, there's a few rules that we have to go over about those electrons, where they are, and how they can act. So first is the Aufbau principle. And that is that electrons always start at the lowest possible energy sublevel. So what that means is they want to be as close to the nucleus as possible. And then once those orbitals are filled, they'll move further and further and further away. So one way to represent this is if my nucleus was down here, for example, the first shell, the one closest to the nucleus, is the 1s. Okay, and that's where 2 electrons can go. And then the next one, if you look at this diagram, would be the 2s, and then 2 electrons can go in there. And then the next one is a 2p, and that has 3 different shells, or orbitals. That's the word I was looking for. This 2p subshell has 3 orbitals. It can hold a total of 6 electrons, 2 in here, 2 in here, and 2 in here. Then comes 3s, and you just keep moving higher in energy. Now, the problem comes when you get past the 4s and all the numbers start getting jumbled, because if you're going from bottom to top, which is what the Aufbau principle says, the order according to this chart would be 4s, and then 3d, and then 4p, and then 5s, and then 4d, and then 5p, and then it gets confusing to try to figure that out. So I am going to give you a way to try to get those in the correct order, but notice after 5s, everything gets a little jumbled. So how do these work? What do these represent? Well, the 1s, the 1 represents the energy level. If we're talking about quantum mechanical numbers, that is the n. Okay, so if I'm talking about level 1, it's a 1. S is the subshell type, aka the azimuthal quantum number, or the L. Remember, we can have an S, a P, a D, or the next one is going to be F. Those are our only 4 options for the type of subshells, those M sub L numbers. And then the exponent here is how you would write it, is the number of electrons in that subshell. So an S subshell only holds 2 electrons. See, it's only one little box. It can hold 2 electrons. That's, remember, when L is 0. So there's only 2 options for M sub S. It's a +1, +1/2, or -1/2, because you can only have 1 of the M sub L's. Now, if you go into a p orbital, say if this was 2p, p orbital can be the M sub L number for p is 1. So you can have a -1, a 0, or a +1 for M sub L. So then that means it's got 3 boxes, so it can hold 6 electrons, and so on and so forth. I'll show you an easier way to remember that in a minute. So what happens is they keep building. So every element on the periodic table, as you go in order, you're adding an electron each time. So the most simple of electron configurations is for hydrogen. Hydrogen only has 1 electron, and it goes in the first orbital, so it is 1s1. Helium has 2, so it goes 1s2. Now, lithium has 3 electrons, so we have to go to the next orbital, and if you follow the Aufbau diagram up, that would be 2s. So this has 1s2, 2s1, a total of 3 electrons. And you just keep adding on and adding on and adding on. So you do have to know how many electrons go in each type of orbital. The S holds 2, P holds 6, D holds 10, F holds 14, and you have to know what order they go in order to get it right. So they're just kind of built. Okay, so another rule that we have to abide by when we're doing this whole electron configuration thing is Hund's rule. And Hund's rule is that electrons like to spread out within a subshell. So if I'm talking about the p subshell, which has 3 orbitals, the electrons like to spread out before they pair up. So we call that the empty bus seat rule, because if you think about it, if you were to get on an empty bus and there's 1 person in a seat, you are not going to sit right next to that 1 person. You are going to sit in your own seat. You're only going to pair up once there is a person in every single seat. So that's why it's called the empty bus seat rule. So if we're looking at here, I've got a d orbital. Okay, these are called degenerate. They're all the same energy. So say this is a 3d. Okay, D holds 10 electrons. It has 1, 2, 3, 4, 5 orbitals in it. Each one can hold 2 electrons. So if I only had 5 electrons to put in here, I would put 1 in each orbital. And then if I had a 6th, then I would start pairing them up. I would put 2 here and so on and so on. So a good example to represent this electron configuration is carbon. So carbon has a total of 6 electrons. So if I start at the beginning, it goes 1s2 and then 2s2, and then I only have 2 more electrons. So in the next orbital, which is 2p, it only gets 2. Okay, and I know that 2p was next because if you follow this diagram, it goes 1s and then 2s and then 2p. So I would have 2 in the 1s, that's the first energy level. The next one is 2s, so I have 2 electrons. And then in the next one, p has 3 places to put electrons, but I only have 2 to put in there. So they spread out before they pair up. So this is actually called an electron orbital diagram. I labeled that over here. Orbital diagrams tell you where the electrons are. As you can see, each of the arrows represents an electron. And the one pointing up, so we draw half arrows just to kind of make it short. The one pointing up represents an upspin arrow or an upspin electron. The one pointing down represents a downspin. So what's going to happen is these 2 electrons here, they're going to spread out. They're both going to be spin up or they're both going to be spin down. It doesn't really matter. They just have to be the same until they start pairing up, and then you get a 1 up and a 1 down. And what does that 1 up and 1 down represent? Well, the plus 1/2 and the minus 1/2 spins the m sub s in the quantum number. So this is really just another, a little bit more visual way to represent what the electrons are doing instead of just using the quantum numbers. Okay, so the more important thing is going to be writing the electron configuration. So that 1s2, 2s2, blah, 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 blah thing. Okay. I am going to show you how to do what's called shorthand, because if you think about it, when you get like down here to these elements, you get like 100 and some electrons, you get crazy long electron configuration. So before I get into the shorthand, I want you to look at this picture here, because I think this is the best way to remember what order the orbitals go in. So you're going to follow just like the regular order of the periodic table. This is hydrogen is number 1, helium is number 2, lithium is number 3, and then you just go on and go on and go on. So the only things that you really have to remember are that these 2 columns here represent the S block. Okay, so if you have an element in the S block, that means its very last part of its electron configuration is S. That's where its valence electrons are. Okay, it's going to end in the S. Okay, now the other thing that the periodic table can tell you is that since there are 2 columns in the S block, S holds 2 electrons. Okay, then I'm going to hop over here. This is the P block, because next after the S, so this will go 1s, 2s, and then next comes 2p. The P block, you will notice, has 1, 2, 3, 4, 5, 6 columns, because P can hold 6 electrons. So as you go across the periodic table, you're just going to add an electron each time. So this is 1s1. This one is 1s2. Then we go to the next one. Then this one has 1s2, 2s1. This one is 1s2, 2s2. This one is 1s2, 2s2, 2p1, and then you just keep adding them to the p until that one's full. And then you go to the next one, the 3s, and then you go to the next one, the 3p, and then you go to the next one, 4s. This is where the numbers get weird. Okay, this is called the D block. The transition metals are in the D block. This has 10 columns, meaning D can hold 10 electrons. So you add an electron to the D orbital until you fill it up, and then the next one is 4p. Now, where the numbers get weird is that this is 4s. The D block actually starts at number 3, even though it's in period 4. So it goes 4s and then 3d, then 4p, then 5s, then 4d, then 5p, then 6s. So if you want to label your periodic table like this, as long as you remember that S starts at 1, P starts at 2, D starts at 3, and then F, the other one, starts at 4, you will be able to get it in the correct order every time. Now, we don't really talk about the F block that often. It has 14 columns, so it holds 14 electrons. These 2 rows actually go right in here between the S and the D. We just pull them out to make the periodic table fit better onto one page of paper. So it would go, the order would be 5S, and then 4D, 10, 5P, 6, 6S, 2, and then 4F, 14, and then 5D, then 6P, then 7S, then 5F, then 6D, then 7P. And those are all of the shells. So if I were you, I would kind of get used to labeling it this way, and then you just go in order to figure out what your electron configuration is. Now, like I said, I'm going to tell you how to do this kind of shorthand. So if you have something really, really big, something down here, what you're going to want to do is find the noble gas, right? Noble gases are in column 8, that is before your element, and put it in brackets. So down here, I'm going to do tin, SN, which is number 50. Okay, it's down over here. So the noble gas that is before tin, if you go up and all the way to the right, it'll give you the one that's before it, is krypton. So the reason that we do this is because noble gases have full electron shells or full electron energy levels. So we can be like, okay, well, I have krypton plus some extra. So krypton is number 36. So this like takes care of the first 36 electrons. And then you start after that. So after krypton, which is right here, next comes the 5s. And then I got to put more electrons in here until I get to 50 because tin has 50. So I do krypton 36, and then I would do 5s2. 4d comes next, that's 10. And then 5p can hold 6, but I only need 2 more to get it to add up to 50. So this is 36, 2, 10, and 2. That equals out to 50. So this would be tin's shorthand electron configuration. All right, so find the noble gas before your element, and then where do you start after that? Well, you start at the next row at the S for the row that your element is in, and then you keep going until you get the right number of electrons. Okay, so these again add up to 50, which is tin's number. Okay, so the periodic table is kind of set up to help you understand what order they go in. If you need help, ask me, but it is always going to follow this order. We have a couple of exceptions that I'm going to talk about here in just a minute, but they do have to add up to the right number of electrons. One thing to point out, whenever you have an electron configuration, the very last orbital might not be full. It's only full, so like P6, if it is a noble gas. Okay. So last thing I kind of want to talk about, like I said, there's a couple exceptions that we need to know about and a couple of vocabulary terms, those being the core electrons and the valence electrons. So this is super important because the valence electrons are the ones that do all the chemistry. I don't think I literally wrote that. It's the outer electrons. They do the chemistry. The ones on the inside don't actually interact with anything on the outside. Those are called the core electrons. They're the ones closest to the nucleus, the ones in the lowest energy levels. The valence ones, however, are the ones in the highest energy levels, whichever ones have the largest N value, right? The energy level. Those are going to be your valence electrons. Okay, so those are a couple of vocabulary terms, and then on to the exceptions I wanted to tell you about. Okay, so these exceptions come in 2 kind of columns on the periodic table. It's chromium and anything under chromium, and copper and anything under copper. So if you're looking at these, right, we add an electron each time. So it went 4s and then 3d. But then chromium, you should be like, well, I thought we filled 4s before 3d. So this should have 2 and this should have 4. And it doesn't. Same thing here with copper. This 4s only has 1. And this 3d is full. And that doesn't make sense according to what I told you up here. It should go 4s and then 3d. Should go 5s and then 4d. So the rows or the columns, sorry, the groups with chromium and copper actually don't follow that rule. And so that's the 3d and the 4s because, well, first of all, they're very close in energy, the 3d and the 4s. So sometimes the electrons don't just stay in one. The other reason, and the most important reason for this happening, are because half-filled subshells are actually kind of stable. And what I mean by half-filled is if you have 4 boxes, so in a d orbital, or sorry, 5 boxes, so in a d orbital where you have 5 boxes, if you have a single electron in each one, it's actually a little bit more stable than any other combination, except for completely full. So like completely full, like copper, this is really stable. This is kind of stable. And anything in between is not that stable. So stability wise, any combination is kind of not really that stable. Any that has 1 in each is going to be more stable, and anything with 2 in each is going to be the most stable. So the reason that one of the electrons moves from the 4s to the 3d is because now all of these are half filled, which makes it pretty stable instead of it being 2 and 4. Same thing down here. Instead of it being 2 and 9, one of these moves over here. So you have 10 in the D block in that D subshell and only 1 in the 4s. So you should know those 2 exceptions. Those might show up on the homework. Other than those 2, everything else is going to follow the rules that we've gone through. So for example, number 10 here, I want you to write the shorthand electron configuration. So that's like the noble gas finish. The orbital diagram, so that's with the arrows, and I want you to indicate the core and the valence electrons based on those definitions we just went on for sulfur, iron, arsenic, excuse me, in indium. So I'm going to talk through sulfur and then you guys can do the others, okay? So sulfur is number 16 on the periodic table. So that means it's going to have 16 electrons unless I say otherwise if it's got a charge or something. So I'm going to start at my 1s and then I'm going to go until I get to 16. So I'm going to look back up here. Oops, at my periodic table, right? So I've got 1s comes first, s holds 2, and then 2s, that'll be 2 more, and then 2p, well, that's 6 more, so now we're to 10, and then 3s holds 2, so that's to 12, and so once I've gotten to 12, my next one is 3p, I need to put 4 in there because then all those exponents add up to 16. I've got 16 electrons. So this is the whole electron configuration. Now, if I wanted to do shorthand, you pick the noble gas that is before sulfur. So up one all the way to the right, that's neon. Neon is number 10, so that takes up the first 10 electrons. So all of these guys. Then you start at the row sulfur is in, so it's 3s2, 3p4. Notice this part is the only part that's down here after that noble gas. Okay, then the last thing I wanted you to do is to draw out, it says indicate the core and valence electrons for the elements, and you're also supposed to draw the orbital diagram. Now I drew the whole orbital diagram. I believe I changed it in your notes to just be to draw the valence electrons orbital diagram because like indium down here is really big. The whole thing would look like this: 1s2, 2s2, 2p6, 3s2, 3p4. Remember, spread out and then pair up. And then I labeled which ones were the valence electrons. Now remember, by definition, the valence electrons are the ones in the highest energy level, the ones that have the largest N value. Those are the ones on the outside. So these both have a value, an N value of 3. So they are all valence electrons. So sulfur has 6 valence electrons. Okay, so I want you guys to try the next 3, and then I'm going to kind of a little bit talk through the answers here. Okay, so iron is argon 4s2 3d6, and I'm like, okay, which ones are the valence electrons? The ones with the largest N. So it's not necessarily the last one, it is the one with the highest energy level value. So 4s2, so iron has 2 valence electrons. This one down here, this would be argon 4s2 3d10 4p3. This is a 4, this is a 4, this is in level 3. So which ones are valence electrons? These ones and these ones. Okay, same thing over here, these ones and this one. All right, so pay attention to which ones are going to be your valence electrons when you write out your electron configuration.